Good morning, good afternoon, and good evening, everyone. Thank you so much for participating in my presentation of the prototype, algorithm-based estimate, an alternate approach of construction cost prediction in the early stage of design. There are 5 sections in the presentation, and we are now at the first section, definition. Here I am, your presenter, Shih-Chi Liu. I'm a pre-construction engineer. Working with Hathaway Dinwiddie Construction Company, one of the largest general contractors in California. As a pre-construction engineer, my main job is construction cost estimating. There are 2 major estimating approaches in the industry. The first one is rough order of magnitude, ROM. By simply averaging all the similar project costs, a reference number can be retrieved fairly quickly. The second approach is detailed estimate. It is self-explanatory that the estimate has to be built up line by line to get the final cost. This prototype aims to keep the advantages while eliminating the disadvantages of these 2 approaches. The problem that is to be solved is how to predict the construction cost based on the project parameters with machine learning regression models. And turns out, the entire pipeline looks more like this. We will go through each and every step in the following presentation. With the pipeline in mind, we move on to the second section, analysis. The first step of data analysis is data exploration. We need to know our data points better in order to properly analyze them. Project features X include both numerical and non-numerical inputs. Numerical inputs are usable square footage, rentable square footage, number of floors, and construction duration. Non-numerical inputs are client type, project scope, project function, and so on. These features are selected based on our domain knowledge as construction practitioners. We believe that they are strongly related to construction costs. Some basic data statistics are presented here. We see project dollar amount as the target Y, followed by numerical inputs and non-numerical inputs. What is noteworthy is that all the non-numerical inputs, as known as descriptive features, are one-hot encoded into 0 or 1 based on whether they are applicable to a certain project. We look into count first. I would like to point out that there are only 117 data points in the dataset, and this is why I code this as a prototype instead of a workflow. The goal is to explore the potential and opportunity of machine learning applications on a real construction problem. That being said, all 4 numerical features have missing data that require extra attention during data preprocessing. Differences between mean and median indicate that data points are not symmetrically distributed. Feature scaling might be required to redistribute the dataset. The coefficients of variation are comparatively high, meaning all numerical data points are scattered. Outlier detection is, therefore, required during data preprocessing. By looking into scatter plots, we understand that all the numerical inputs have strong relations between project cost, especially USF and RSF. The discovery is aligned with industry practice. In the early design stage, it is very common that people multiply the amount per USF or RSF by the size of the project to generate a quick number. We can see all 4 numerical features are heavily skewed and are not properly normalized. Most of the points tends to be smaller numbers. However, the dataset also contains a few much larger numbers. Data transformation with a certain scale, along with data normalization, might be required during data preprocessing. With basic understanding of data, it is time to decide which models we are going to use. According to scikit-learn algorithm cheat sheet, with more than 50 and less than 100k data points, and with more than a few important features, ridge regression, ensemble regressors, and SVR are selected. In addition to these models, I add 4 more commonly used regression models to the list. With the knowledge of data and models, we are on to the third section, methodology. Data preprocessing is a fundamental step to assure the model reliability through cleaning, formatting, infilling, and scaling the raw data. 5 preprocessing steps will be performed sequentially to help with the prediction outcome based on the understanding of data characteristics in the previous section. The first step is escalation. The process is to convert project amounts entered in various years to today's dollar. Several construction cost indices are referenced and weighted to generate the index for our own need. Based on data exploration and missing metrics, we understand that several missing data points exist. There are multiple ways to deal with this issue, and the mean values are chosen to fill the white spaces. Again, based on the distribution plots, we realize that all the numerical features are not distributed normally and heavily skewed. One of the best approaches for the issue is data transformation, and one of the most commonly used methods is natural logarithmic transformation. After the transformation process, they are more alike normal distribution, and those outliers will have much fewer negative impact on machine learning algorithms. That being said, according to the previous scatter plot, there are still a few outliers in the dataset even after feature scaling. The method of standard deviation / z-score is chosen to detect and remove outliers. The thresholds are set to be plus and minus 2.5 times of standard deviation from the mean value, in which 98.7% of the data points will be kept. 5 data points located outside of the 2.5 standard deviation boundaries are then be removed. The last part of data preprocessing is normalizing numerical features. This is to make sure that all the features are within the same scale, that is to be between 0 and 1. With well-processed data points, it is time to shuffle and split them. Both features and target will be split into 2 subsets as training and testing with the certain ratio. 80-20 in our case here. Validation set, on the other hand, will be split and manipulated later to fine-tune the model. We are going to train the training set. In here, the training pipeline is coded with its maximum flexibility. The inputs of the pipeline are learners, sample size, and of course, training and testing sets. The outputs include learners, training size, and the affiliation scores. So, what is the affiliation matrix? R2 score is the most common metrics for performance affiliation. It is represented as 1 minus the ratio of mean squared errors of the machine learning model in the simplest model. Typically speaking, the range of the score is between 0 and 1, and a higher score indicates a better model. The performances of 7 models are affiliated by the metrics of R2 score as shown in the table. The chosen model is the one with the highest R2 score, and that is XGBoost. XGBoost achieved 0.99 in training set and 0.78 in testing set. The model is most appropriate for the task of predicting construction cost based on the given data. After choosing the best model, XGBoost will then be fine-tuned to achieve its optimized performance using grid search technique. Make a table, think of all possibilities, and pick the best one. XGBoost has multiple hyperparameters, and through the tuning process, the optimized combination of those can be determined. The highest score of 0.73 occurs with the combination of n estimators as 100 and max depth as 2. With all that, I present you the best and optimized model. Onto the fourth section of the presentation, the result. Firstly, we're going to affiliate and validate the best and optimized model. Prior to the optimization process, XGBoost achieved 0.78 R2 score with the testing set. After fine-tuning the selected model with its hyperparameters, there is a 19% performance increase from 0.78 to 0.93. And now, the optimized model and its performance will be compared to two benchmarks to justify whether it passes the performance threshold. The first benchmark is our current approach of leveraging Hathaway-Dinwiddie historical data. The existing method in our pre-construction team for cost prediction is as straightforward as filtering and averaging. The R2 score calculated by filtering with client type is 0.79, by project scope is 0.86, and by project function is 0.80. These are not big numbers. This might explain why rough order of magnitude is still one of the dominant estimating approaches in the industry. The existing workflow seems to do a decent job by only looking at its R2 score. However, it is not a robust model due to overfitting. The second benchmark is the simple algorithm-based approach. In our case, it is linear regression. The R2 score is as low as 0.40, and since the optimized XGBoost has the score higher than both of the benchmarks, it is a justified model. We will then publish the best performed, optimized, and justified model. By feeding new project features into the published model, we will be able to predict its construction cost and to retrieve the new result. After going through the entire machine learning pipeline, it's time to conclude the prototype with some reflections and improvements. How can we do better with the current pipeline? The most fundamental yet difficult issue is the size of dataset. Currently, there are only 117 datasets, and I would definitely like to have more and more data points to be able to build a more robust machine learning model upon, so that this could no longer be just a prototype, but a practical estimating workflow. We can also take a closer look at the inputs. Instead of having usable square footage, rentable square footage, number of floors, and construction duration as numerical input, room-related information could be more relevant. Room count can determine door, equipment specialty, and fixture quantities. Room area is strongly related to floor and ceiling areas, and fire sprinkler and HVAC zones. Finally, room parameter could have direct impact on drywall and glazing length, as well as wall finish and window treatment quantities. Furthermore, instead of only having one lump sum construction cost as the target, we can ask machine learning models to generate trade level details. And how can we improve the existing pipeline to have a better performed model in the future? Building a machine learning workflow is a trial and error process, and all the opportunities are what make this a science. Since there are lots of features along with the expansion of dataset, hopefully the training time could increase fairly quickly. When we reach the point that the model takes a longer period to train, we can consider to extract features and to only train the model on the most impactful ones. And currently, all the codes and supporting files are saved on local computer. However, the ultimate goal is to provide access to the entire company. Keeping everything on the cloud is necessary. There are a lot of solutions, including Amazon Web Services and Azure. An integrating data visualization platform like Data Studio, Power BI, and Tableau could also be a big add to the pipeline. The front end must be built since the expectation of all users knowing how to play with codes is not realistic. There are multiple ways to construct the user interface, including web browser and APIs through Autodesk Forge. And with all that, the prototype of algorithm-based estimate is presented to you. Your participation is much appreciated. I'm looking forward to any feedback, questions, and comments. Thank you so very much.